We now discuss the concept of Karnaugh maps, which is a method of simplification of logic functions using Boolean algebra laws. But we observe that those laws, when you apply them like we have done in a previous example, is that they can be rather cumbersome and not intuitive. And we see that a more suitable method developed by this gentleman called Maurice Karnaugh in 1953, called Karnaugh map method, provides some intuition in terms of simplification of logic functions. And this method is quite popular with fewer variables between 1 and 4. When you get beyond 4 variables, again you need some other methods, but for the time being, 4 variables are adequate. In short, it is called K-map method, so don't confuse it when you hear K-map. And we see that although the technique is quite useful or may be used with 5 or 6 variables, it becomes rather cumbersome and is rarely applied. In the event you want to do 5 or 6 variables or more, another method called Quinn-McCluskey method is often used, but we are not going to look at that because it's beyond the scope of our course objectives. So we work with the 4 variables for illustration of simplification of variable Boolean expression. So we start with an example that will allow us to illustrate a 4 variable Karnaugh map. And you see that a logic expression with 4 variables is simplified with the aid of 16 cell K-map. So we will see now a 16 variable K-map that allows us to solve or to simplify it using the Karnaugh map method. So let's consider an example of a Boolean expression written as y is equals to a, b, c, bar, d, bar, or a bar, b, bar, all the way up to here without necessarily repeating. We won't use the 16 K-map method to solve it. And we say that the 16 cell K-map will consist of 4 rows and 4 columns. And we will divide the 4 variables, 2 to become rows and 2 to become columns. So that with 4 variables, A, B, C, D, a total of 6 combinations are possible. Starting with A, B, C, D, then we start introducing the bars, and we'll see that how that happens. So we now look at this example or this Karnaugh map method, in which case we are dividing the most significant 2 variables A, B to become the rows, and the least significant bits C, D become the columns. So that is how we normally arrange the 4 variables. If you are given variables P, Q, R, S, the 2 most significant variables, you put them to become rows, and the 2 least significant variables becomes the columns. So once we have done that, we use the gray code to represent the variations of the 2 variables A and B. So we start with 0, 0, 0, 1, 1, 1. So notice that we are not going to 0, 1, 0 and then 1, 1. Notice that all the time when we're using K-map, these 2 variables are interchanged. And they're not interchanged as such, it is because we are using the gray code that we introduced earlier. So on the same manner, we start with 0, 0, 0, 1, 1, 1, and 1, 0. That is the most important observation that you'll need, particularly when you are dealing with the K-map. We always use the gray code. We see that the variation 0, 0, 0, 1, 1, 1, 1, and 1, 0, we observe that only 1 bit changes, just like we observed with the gray code representation. And we also say that the variation of the second set of variables CD is considered and it is entered vertically and adjacent to the first column. The variation is again in that order of 0, 0, 0, 1, 1, 0, and 1, 1, and 1, 0. This nomenclature enables each of the 16 cells in the 4 variable K-map to have a distinct decimal identity. And we will now see how we normally give these numbers. You can even memorize, becomes quite straightforward, that we always count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What you'll observe is that the third row and the third column is always skipped. So again, let me repeat it. You'll see 0, 1, we are always keeping the third one and reading it as last one. So 0, 1, 2, 3, 4, 5, 6, 7. We reach our third column. and then we go to the fourth one, 8, 9, 10, 11, until we have the final one. That is the way we normally label the K-map. So as we have said, we normally say that the variation of variables a, b, and c, d follow the gray code representation, which follows for both the variables a, b, and c, d. So for illustration purpose, I would want to use K-map to represent the variable that we made earlier on a K-map, so that we have y is equals to a, b, c, d bar bar, or a bar, b bar, or c, d, or a, c bar, d, or a bar, d, like that. So if you are given such a Boolean expression and you are told to represent it using the K-map, what you do is to make sure that you know what each of these variables represent, and when they are not represented in such a variable, how can you represent such? So what, for instance, you know that whenever you find a bar, b bar, you notice that there is two variables that are missing, because these are four variable expression. So you know we are missing c, d, and therefore what we say is that the CD can take the four possible values, meaning you can have CD, you can have C bar D bar, you can have C D bar, you can have C bar D. These are the four variables that may be added to represent this one. So for instance, because we have made that before, we don't now need to do this one using the simplification methods that we made earlier of applying the axioms of Boolean algebra or the De Morgan's theorem. All we need to do is to know that this column is 0, 0 for AB, and that is equivalent to A bar, B bar. So as we said with K-map for variable 1, we say this is A, B, this is C, D. So this means 0, 0, 0, 1, and 1, 0. Similarly here, and we know these variables or these values are equivalent to A bar, B bar, A bar, B, A, B without any bar, and A, B bar. Whenever you have a 0, is equivalent to a bar. Similarly, C bar, bar, C bar, D, and C, C, D bar. And therefore, whenever we make this one, we are being told that it is a 1 in this column, and all of these are the other variables. So we will fill this one as 1, 1, 1, 1. And I will mark this one like I have already filled that one. So then we have A, B, which is this column, and C bar D. So it is this cell. Where these two intersect, we have this and we have this. Where they intersect, this in the first row, that column, you fill a 1 there. That one I have filled. Then you have C, D without any bar. It has no any other variable. That means the entirety of this row is going to be equivalent to 1. And that one I mark it as filled. A, C, B, D. So what we are missing here is a B. So all we need to do is identify the columns that have A without a bar, and these are these two columns. And then we notice that we have C bar D. C bar D is filled in the second row, meaning that here we have a 1 and here we have a 1, because these two intersect where we have A without a bar and B may take of the two possible values. And therefore this one I have already done that. And finally A bar B is found in this column, and D is found where we have D without bar is found in the second row and the third row. So where those two intersect, that is between this and, remember where I put these blue rows, that means this is where they intersect, and you put a 1 where these two, because this already has a 1, then I only add 1 in the one that is missing a 1. So that is how you represent this function y. And therefore, if you now were to do the grouping, which you'll do at a later stage, you will see that you can form some groups of 8. But for the time being, because we have not introduced, all I wanted to do in this slide is to show you, if you're given an expression that is as such, you want to feed it using the K-map method, you just need to identify where each of the variables can fit. So just like we have done, I have just shown you how we can feed in that variable, that expression that I had here. And as you have seen, we are having the cells filled just like I have shown you in the previous example. And therefore, that should be adequate to illustrate how we are coming up with the ones and zeros. Of course, I think I never mentioned that when we have finished filling the ones from the variables represented here, then all the cells that don't have ones, you fill them with zeros, just like you can see here. So we want to look at the simplification rules that are used with the Karnaugh map method, and we normally consider that each cell in a Karnaugh map has 4 cells neighboring it, and these cells are on the immediate right, immediate left, at the top, and at the bottom. And for example, cell 7 has cells 15, cell 3, cell 5, and cell 6 neighboring it. So as you can see, we are talking about this cell. So looking at the simplification rules, this is what we refer to as cell number 15, and we are saying that each cell is neighbored by 4 cells always, whether it's at the center or whether it is on the edges. And remember, we named these cells with their numbers, which we are putting in them at the top left: 0, 1, 2, 3, 4, 5, 6, 7, etc. So we are considering cell number 15, and we can look at its neighbors on the vertical and horizontal sides. So from the horizontal side, we have cell 13 neighboring it. The bottom side, we have cell 14 neighboring it, cell 11 neighboring it, and cell number 7 neighboring it. And again, if you look at cell number 7, you'll see that it is neighbored by 5, 3, 6, and 15. Cell number 10 is surrounded. Now, this is where things have become a bit complex, but you just need to be attentive, and you'll see that we can consider this cell to be still surrounded by 4 cells. First and foremost, the straightforward ones is 14 and 11. But if you are to fold this K-map to form this edge, to form a cylinder, this edge would come to this side, and therefore this 10 would be, okay, not 10, this cell would be touching this one, be touching this edge here, and therefore this 10 would be neighbored by 2. And on the other hand, if you are to fold it horizontally, you'd see that this edge would touch this edge, and therefore this edge would touch here. And for that reason, number 10 is now neighbored by cell number 8. And therefore, the neighbors of 10 are 14, 11, 2, and 8. That is what we are saying in this slide here. So that the neighbors of 10 are 2, 4, and 8. The numbers of 7, just like I mentioned, is 15, 3, 5, and 6. We always, the key idea here is that you can consider the cells are on the edges. You can form a horizontal cylinder or a vertical cylinder. And therefore, the ones that are on the edges, when you form the cylinder, what touches them becomes their neighbor. So as you can see, here we have a horizontal cylinder that we can use to illustrate that combination or that neighborhood. The neighboring cells to those at the edges are identified easily by viewing the K-map as a cylindrical surface. So that is the point that I have quite belabored. And now we want to look at how can we form groups, so that the groups are the ones that help us to simplify our expressions. For instance, we had said that we can have 1 there, 1 there, 1 there, and 1 there. So in the event that you have such an expression y that is giving you ones in those cells, then you normally say that you can form one group. And this group, you give it an expression probably representing A, B, C, and D. And therefore, if this was A, B, and C, D, you can give this expression. Therefore, you see that is what simplifies your expression. So we have some rules that are used to form the groups. And we say that in a 4-variable K-map, we apply the following rules. We start by forming the biggest group of 16. So if you can have a 4-variable expression that is feeding all these cells, that is considered a trivial case in which that all the cells are filled with symbol 1, and that means your y, like we met earlier, is equivalent to a 1. So in the event that you find that all the cells are filled with 1, that forms what is called a trivial case, and it is all the cells are filled with 1 entries, and the expression is said to be equivalent to true always. Otherwise, we always check where we can form groups, and if we can't form a group of 16, then we look for the next biggest group. Can we form a group of 8? Or can we form a group of 4? Or can we form a group of 2? Or can we form a group of 1? So we normally never form groups of odd numbers that are not to base 2. Remember, these are the numbers that are to base 2. So we don't look for groups with 3 cells or 4, 5 ones or 7 ones. We normally work with, we can either form a group of 16, the one we have called the trivial case, or the group of 8, the group of 4, 2, or 1. So these group rules can be summarized as follows. In a 4-variable K map, the following cell group numbers can be formed: 16, 8, 4, 2, and I also mentioned 1. The cells in a group must satisfy the 2 conditions of neighborhood and same cell entry. So if you can say that we have a 1 there, we are never forming groups of 1s and 0s. It is either 1s, and when we are talking about some advanced concepts of product of sums, which we will talk later, we can also form groups of 0s. But for now, let's just understand that we are talking about groups of 1. So the procedure for grouping a 4-variable K map is as follows. We check for trivial case when all the 16 cells have 1 entries. Otherwise, when they don't, we can look for a group of 8, and when we do not, we can look for a group of 4, etc. And we normally circle them, and we will see that in an example. And you also notice that a cell can be part of 2 or more groups. And I think in this example, we are saying that if we find we have ones that are following probably something like that, so we are saying that in the first rule, form the group of 8 and circle it. That is what we mean when we say we are forming a group and circling it. Then if we find there is probably 2 more cells there that are having 1 entries, then you don't really say that these are alone. As long as they are neighbored by other 2 cells belonging to another group, you can still form another group that will make a group of 4. Or if you find another 1 there and another 1, we can say that this group is, if you form a cylinder, this will form a group, and you circle it as such. So in few words, you can form groups of 4. For instance, you can have 1 at that corner. You can form a group of 4 that we normally arrange like that. That is one method, because you might consider like this is an edge. If you form a cylinder here, this will touch this one. And if you form a cylinder horizontally, this edge will touch this edge. And for that reason, the 4 corners with 1s are considered to form a possible group. That is number 1. The other one that is quite straightforward is the one that I showed you. If you have entry cells with entries at 1 there, you can form a cylinder here, and you can say that this is a group that is a group of 4 ones. Similarly, you can form a 1 there and a 1 there, and you can form a group of that form, because this is a cylinder. And similarly, you can form a group of 8. For instance, you have 1, 1, 1, 1. Again, you can form a cylinder, and this edge will touch this edge, and for this will be a group of 8. So all those are possibilities, and I think that they are well introduced. So just like I have illustrated, if you find yourself with such a grouping like we did earlier, this is the Boolean expression that we had met earlier. The only thing we never did was to group the cells. We had ones in these 4 positions or these cell numbers, and therefore what we remained was now to perform the groupings, and then after we have formed the groupings, we assign them their equivalent Boolean expression, which in this case we can see that this is one group of 8. This is the one you form first. Then after that you can see there's a group of 4 that can be formed here, another group, and we have one more that is left here unformed, which the only one we can group is 1. So the other thing that we normally do with the K-map is to give them values, and like you can see that is being done here is that we look for, in this group we normally ask ourselves what variables are not changing in their value, the entirety of the group. So for instance, we can remember that this was AB, this was CD, and this one is 0, 0 for AB, representing A bar, B bar. So in this whole group of 4, A, B remains the same, or A bar, B bar remains the same, whereas CD is changing from 0, 0, 0, 1, 1, 1, and 1, 0. Therefore, what we normally say that this group can be represented by A bar, B bar, what is not changing. And that is what we have, you can see being represented there. Then we can look at the group of 8, this group of 8, what is not changing. And what you can be sure about is that to go through the entirety of these 4 columns, A is always changing from A to A bar, and B is changing from B bar to B, etc. So we will not have any B there. Similarly, we can also see that D is changing from being C is changing from being a 0 to a 1, and therefore the only thing that is not changing is this that remains a 1 in this entirety of this group, which is D. And for that reason, we are saying that that group represents a variable D because all the others are changing their value, while D remains the same, and the value of that D is a 1, not a D bar. And finally, we look at this one. This one is represented by 0, 0, 0, 1, 1, 1. So in this case, we have A, B. So A is not changing, B is not changing, but you can also observe that C is at 0 state, whereas D is changing from 0 to 1. Therefore, we will not work with the one that is changing, but rather on the one that is not changing, which is a C. Therefore, it's a C bar. You can see the status of C is 0, meaning we can give this one to be C A B C bar. And for that reason, that is what you can see, that this group is represented by A B C bar.